So at this point in Chapter 7, we've gone over centripetal acceleration. Now we're moving on to look at Newton's law of universal gravitation. We define gravitational force as the mutual force of attraction between particles of matter. So we can sort of think of this in terms of centripetal force, which we learned about in the last section of this chapter. If you visualize a cannon shooting a ball so fast that it goes into orbit around the Earth, some centripetal force with a net direction in towards the Earth must be keeping this ball in a circular orbit. That force is the gravitational force on the ball. This is Newton's law of universal gravitation. It says gravitational force, which is written here as F sub g, is equal to g, this is capital G rather than lowercase g, and it's the gravitational constant, and it's defined as 6.67 times 10 to the negative 11th, and the units there are newtons meters squared over kilograms squared. And then we have m1 and m2, which are the masses of the two objects involved, divided by r squared, and r is the radius between them. Let's take a look at how this works. So we know from experience that gravity is a field force. In other words, the objects do not need to be in contact for gravity to be acting on them. Gravitational field strength is defined as the magnitude of the gravitational force exerted on a unit mass. So we can sort of simplify this. We can take Newton's second law, F equals ma, and we'll redefine it for situations with gravity. So Fg, or gravitational force, equals m times g, which is free fall acceleration. Then if we simplify some things, take them over to the other side, we get that g equals F sub g, or gravitational force, divided by mass. In other words, an object's free fall acceleration equals the gravitational force on that object divided by its mass. And just some quick notes about gravity. It's a vector force, meaning that it has both magnitude and direction. And its direction depends on gravity, so gravitational acceleration. And as we've already seen from previous chapters, this g over on this side is equal to the rate of free fall acceleration, or 9.81 meters per second squared, which we sometimes round to 10. Gravity is critical in determining the weight of objects on a planet. Weight changes with the rate of free fall acceleration, which in turn changes with location. So, in other words, the radius, or distance, of an object from a planet will affect its weight and how fast it accelerates. So we have this equation for gravitational force. It's equal to g times m1 m2 over r squared. Now we also know that the rate of free fall acceleration, g, is equal to gravitational force divided by the mass of the object. So now we'll plug in, we have our two objects, m1 and m2. We'll call m1 the Earth and m2 the object. If we divide the whole thing by the mass of the object, these two cancel, and we get that the rate of free fall acceleration, or g, is equal to big G, again this is the gravitational constant, times the mass of the Earth divided by r squared. And if we plugged in the mass of the Earth and the radius of the Earth here, we would get that this is equal to 9.81. Let's do some practice problems. Number 1. Find the distance between two 0.8 kilogram balls if the magnitude of the gravitational force between them is 8.92 times 10 to the negative 11th newtons. And just a quick note here, from now on I'm going to be using this capital E to represent scientific notation. That's just sort of a calculator notation. So 8.92 e negative 11 is equal to 8.92 times 10 to the negative 11th. Just keep that in mind. So now let's set up our equation. We have these two balls, and we know that this gravitational force, or F sub g, will be equal to g m1 m2 over r squared. And we're solving for r because that's the distance between them. Now we have our 8.92 times 10 to the negative 11th. We know our gravitational constant, that's about 6.67 times 10 to the negative 11th. m1 is 0.8, m2 is also 0.8, and r is what we're solving for. Now this involves quite a bit of algebra, but I've simplified it by dividing both sides by 6.67 times 10 to the negative 11th, and then I've multiplied the r squared over and divided this 0.8 squared by the number of the other side. Finally, take the square root, simplify, we get that r equals 0.7 meters. That's how far apart these two balls are. Number 2. A 66.5 kilogram person stands on the surface of Mars, which has a mass of 6.42 times 10 to the 23rd kilograms and a radius of 3.4 times 10 to the 6th meters. What is the magnitude of the gravitational force that the person experiences? So we're solving for gravitational force, which means we'll set up this same equation. Gravitational force equals G m1 m2 over r squared. This time we have all of the numbers on the right side to plug in. So we know G, that's 6.67 times 10 to the negative 11th. M1 will be the mass of the person, so that's 66.5 kilograms. M2 is the mass of Mars, which is 6.42 times 10 to the 23rd kilograms. And then on the bottom we have radius squared, so that's 3.4 times 10 to the 6 meters squared. Now if we simplify all of this, we get that the force of gravity that's acting on the person is approximately 246 newtons.